Right, hi everyone. So this video is on the reverse chain rule, which as the name suggests, it's the reverse of the chain rule. So rather than differentiating using the chain rule, we're going to integrate something that has been chain ruled already. So we're going to go backwards, which is the complete definition of integration in the first place, the opposite of differentiation. So what I've done is I've written the differentiation table on here on the right. So how do we start these problems? So I'm just going to do this basically through example, and we're going to use this system GDA, right, which this stands for guess, differentiate, and then adjust it. Okay, so how reverse chain rule works is we're going to guess what was originally differentiated, we're then going to check it through differentiation, and then we'll adjust as necessary. So let's see what we've got here, sine 2x. So how do I start an integral? I'm always going to write I equals, so I'm going to let I equal sine 2x, right? I have to just rub that out, it's not very clear. Okay, and remember we have to put the dx in there, so sine 2x dx, right? Even worse. Anyway, sine 2x. Looking at our differentiation table, right, and this is what your objective is. You're always trying to make something look like the right-hand side of your differentiation table, and then you can work back. So for example, cos x here, if I integrate cos x, I get sine x plus c, remember? So if I integrated 2 cos x, can you see I could just times the right-hand side and the left-hand side by 2. So 2 cos x would go back to 2 sine x, you see? So the constants can move around. So if I'm trying to integrate minus sec squared, well, if I just put the minus on the tan x, so I haven't actually changed the relationship between the two, you can see that minus sec squared, if I integrate that, would go back to tan x, right? Back to minus tan x. So let's do the same thing here. Here I've got sine 2x, right? And from my differentiation table, I know that minus sine x goes to cos x. So I'm going to guess that the integral of this is going to be something to do with cos, not x, cos 2x. So cos 2x plus c. You see, that's my guess. It's a guess though, and it doesn't matter if my guess is wrong. What matters, so I'm going to box my guess, right? What matters is my checking, my derivatives. I know this isn't right because if I differentiate cos 2x through the chain rule, cos function goes to minus sine function, and then the derivative of the function pops out, the 2, yeah? So here, I've got minus 2 sine 2x, but that's not what I started with. So I need to adjust, which is the next step of the process, your final answer. How do I adjust? Well, this has a minus 2 in it, so I'm going to need to take my answer here and divide that by minus 2. So you see, minus a half cos 2x plus c. So there's my final answer. So I equals that, right? So that's our adjust phase. And again, you can differentiate that to double check whether that's correct. If I differentiate that, cos function goes to minus sine function, so that cancels the minus. The 2 will pop out. Yes, I'm back to where I started with. Let's try number 2. This time, I've got, again, I equals 1 over 3x plus 2 dx. Now, again, looking at the right-hand side of our differentiation table, does this look like anything we've done before? Well, it kind of looks a bit like the ln, doesn't it? The ln f of x. Because ln f of x differentiates the f dash of x over f of x. So, in other words, if there's a multiple of f dash of x on the top, then this must be a ln problem. And there is a multiple, isn't there? Because if I look at f of x as 3x plus 2 and differentiate it, that is 3. 1 is a multiple of 3, right? So I reckon, and in general, this is our way of looking at things. If you're integrating a fraction, the first thing you're looking at is it ln? Is it ln f of x? Okay? So I'm going to guess that my I is ln 3x plus 2. But really what I should be doing is I should be putting mod signs on it, and we'll talk about why we need to put mod signs on it for Ln. But in general, any Ln integral should have mod signs on the outside, and we will talk about that in class. So plus c. So that's my guess, right? So I'm going to box my guess, and then I'm going to differentiate it to check. So if I differentiate this, Ln of 3x plus 2, so that's Ln of f of x, so that's f of x on the bottom, f dash of x on the top, that's 3. So I've got 3 too many on the top, right? I need 1, but actually I've got 3. So what do I need to do? I need to adjust. I need to divide my answer by 3, okay? So that's where you can put in your adjust box, I equals a third Ln mod 3x plus 2 plus c. Okay? Let me just... this board is rubbish. So, I equals a third Ln mod 3x plus 2 plus c. And again, that can be differentiated to check. Let's move on to our next problem. And we'll make this a bit bigger. Actually, I can't do that because I can't get the pens. Okay, so this time I'm integrating 3x plus 2 to the power of 5. Right? 3x plus 2 to the power of 5. Now, again, reverse chain rule. Think about if this had already started by being differentiated, and this is what it end up as. What do we start with, right? Think about the chain rule. The chain rule says if you have y equals f of g of x, right? So your function within a function, then dy by dx would equal the derivative of the function times by f dash of g of x, remember? Right? So reverse chain rule, essentially how it works is there, if we can see that the thing is in this form, then we can integrate it back to the original chain rule here. Do you see? i.e., is there a g dash of x on the outside of this thing here? It looks like the answer is no, but actually there is a number 1 on the outside. And like I say, if this is g of x, right, the differential of g of x is 3, is that a multiple of 1? Yes, therefore it is a reverse chain rule problem. So let me just make that clear. If there's a multiple of the derivative of the inside out here, then this is a reverse chain rule problem, which means I'm going to immediately guess my function to the power, right? So 3x plus 2, add 1 to the power, divide by new power, right? So I'm going to do it with my hand. Essentially, I'm covering up the thing on the outside because I've recognized that it's a reverse chain rule problem. I add 1 to the power and then immediately divide by the new power. Okay, box that off. And again, we're differentiating to check. So chain rule, the 6 would come down, so that cancels the 1 over 6. That's perfect. So that's 3x plus 2 to the 5 now. And then we would differentiate the inside and a 3 would pop out. So actually I've got 3 too many than what I needed. So I need to divide by the 3 as well. So when I adjust, I'm not dividing just by 6 anymore. I'm divided by 1 over 6 times 3. So 1 over 18. 3x plus 2 squared to the power of 6, sorry, plus c. This board really is crap. Apologies about this. Right, 3x plus 2 to the power of 6 plus c. Okay, and then we'd box that off. Fantastic. And again, if we differentiate that to check, that does work. The 6 comes down, the 3 pops out. Perfect, right? Number 4, this time, so again, just loads of examples. Number 4, I say we're integrating this one, so 1 over 3x plus 2 to the 5. Again, our order of thought, it's a fraction. The first thing we're thinking is this ln f of x? And the answer is no, because the top is not a derivative of the bottom. If I differentiate that, the 5 would come down, 3x plus 2 to the 4, 3 would pop out. That's not a multiple of 1. Okay? So this is not not a learn problem. This is a reverse chain rule problem. So what I need to do is I need to write our power to the 5 as the power of minus 5. And now we're back in the situation that we were at on question 3, because the number next to this is 1. And is 1 a multiple of the derivative of the inside? Yes. So what do? We guess, right? So G colon, we guess, we put our hands over the thing on the outside because we know it's a reverse chain rule problem. 3x plus 2, we add 1 to the power, so that's minus 4, right? Okay, I'm never using this board again. Add 1 to the power, that's minus 4, right? And then you're going to need to divide by the new power, so minus 1 over 4 plus c, right? So we'll box off our answer there. And then we differentiate to check. So the minus 4 would come down. That does cancel the minus 1 over 4. Brilliant. That would be 3x plus 2 to the minus 5. That's what we want. But then when we differentiate the inside, the 3 would pop out. And again, that's 3 too many. So we would have to adjust by dividing our answer by 3. So minus 1 over 12, 3x plus 2 to the minus 4 plus c. Always differentiate your answer again to check whether you're correct. But what we're starting to do is we're starting to build up an order of thought. Okay? So when you're presented with an integral, it's like, well, what do I start with? So if I'm integrating a fraction, right, my first thought is it ln f of x? If it's not ln, can I bring the power up like we did here to make it reverse chain? Okay? That's your thought process so far. Is it ln if it's a fraction? If not, can I bring that up? Right? And then, if that is using the reverse chain, is it in the form g dash of x times by f dash g of x? And if it is, it's reverse chain, right? I.e. that whole is the thing on the outside a multiple of the derivative of the inside. And let's carry on. So this time we've got e to the 4x plus 1. So I is e to the 4x plus 1. Okay? Now e to the 4x plus 1, again, is this, looking at our differentiation table, we know that e to the f of x goes to f dash of x e to the f of x. So is this in the form, on the right-hand side, of f dash of x e to the f of x? Yes, because next to it is again a 1. And is 1 a multiple of the differential of 4x plus 1? Yes. So I'm going to guess, I'm just going to cover up that 1 and go, oh, e to the f of x integrates to e to the f of x. It doesn't matter if my constants are wrong at all. What matters is the checking. Am I checking it? So I differentiate it. E to the function goes f dash of x r e to the function. So here I've got 4, when here I need 1, so I've got 4 too many. So to adjust, my final answer needs to be I equals a quarter e to the 4x plus 1 plus c. Don't forget the plus c, that will cost you 1 mark every time. Number 6, should be getting much faster now. So I equals sec squared 3x plus 2 dx, right? Now, what differentiates to sec squared? Well, it's tan, isn't it? So I'm going to guess that immediately I'm straight into tan. I know tan differentiates to that. So tan function plus c. And again, that's my guess for my integral. So I equals that. I need to differentiate it to check though. So if I differentiate it, tan goes to sec squared. So that would be my D part. And you'll see that the 3 is going to pop out. So hopefully you're screaming at me saying, well, it's got to be 1 over 3. Okay, as your final adjusted value. Let's keep going now. So notice we're going a bit faster. So sec squared x tan to the 4x. So we've got a product, right? That's kind of what I'm getting at here about this whole g dash of x, f dash of g of x. If something's in that form, that is a product, isn't it? You've got one thing times by another thing. So is that thing being times the derivative of something else, right? So here, sec squared x tan x to the 4 is the derivative of one of these things next to each other, basically. You might not be so obvious, but what happens if I wrote this like this and put the 4 on the outside? Then yes, you can totally see that the derivative of tan is sec squared, and that is on the outside. Can you see? Our g of x is tan, our f dash of x at the moment is that whole thing to the power of 4. So what do? It's exactly the same process. I cover up. So I'm putting a cross through here because I can't show you a hand going up on there. So I cover that thing up. I raise it to the power by 1 and then divide by a new power plus c. Okay? Put a box around it, equals signs. And what do? I differentiate it to check. So notice all I did was I added 1 to that and divided by it, right? So if I check, if I differentiate this, the 5 pops down. That cancels, that's great. So that becomes tan x to the 4. Differentiate the inside, and the sec squared x falls out. So I'm perfectly correct here. Do you see? Number 8 is very similar, and there's a couple of ways you can do it, but I'll just do one way. So sine x times by cos x. Again, pick the function. Pick that as your f dash of g of x, let's say. So in this case, it would be cos x all to the 1. Is the derivative of the inside on the outside, or some multiple of it? Yes, because cos does differentiate to minus sine. So I'm going to guess by putting a cross through that. Since I put my hand through that, please don't actually cross your work. I'm going to put my hand over that, raise 1 to the power, and divide by the new power plus c. Okay, so that's my I. But I need to differentiate to check. So if I differentiate, the 2 will come down, that's great. Cos x to the 1. But then cos would differentiate to minus sine. So I need to put a minus in there to cancel that out. Do you see? That's your adjusted figure there. I hope that makes sense to you. And you could come up with another version of that if you let sine x be the f dash of g of x. And there's just a few more examples now. So I know this is going on, but this is really going to help. So let's say I've got I equals minus 4 sec squared 2x over 1 plus tan 2x to the 4. Now this looks horrible, but again, if you know your order of thought, right? If you know the order of thought is this is a fraction, is this a Lund problem? I.e., does this bottom bit here differentiate to the thing on the top? The answer is no, because the 4 will come down, and then the whole thing to the power of 3, and then out will pop the sec squared. So no, it's not. So we go back to our list. Remember, if we're integrating a fraction, our first thought is ln f of x, and then after that, we're going into reverse chain by putting the power back up. Okay, so actually this is minus 4 sec squared 2x, and then 1 plus tan 2x to the power of minus 4 dx. Do you see? Now, is this a g dash of x problem? Yes, because this is f dash of g of x. If I differentiate the thing on the inside, do I get a multiple of the thing on the outside? Yes. So I'm going to guess by covering up this bit, remember, just with your hand, add 1 to the power, and divide by a new power plus c. Okay? It's always the same. and then differentiate it to check. So there's my box guess here. I'm going to differentiate it. So the minus 3 will come down, okay, and that will cancel my third. That's great. So I get 1 plus tan 2x to the minus 4, and then out will pop the derivative of 1 plus tan 2x. Tan 2x goes to sec squared 2x, but times by 2, which is not what I started with. I started with minus 4 sec squared 2x. So I need to times my whole thing by minus 2, what I guessed, right? So my adjustment is I equals 2 over 3, 1 plus tan 2x to the minus 3 plus c. And you quickly differentiate that to check. Does that work? Yes, it does. Therefore, we're correct. Okay? Number 10, very similar story. I'll just clone this. So number 10, very similar story. Except this time, there's no power here, notice, right? So there's no power. So I is minus 4 sec squared 2x over 1 plus tan 2x. So again, you got your fraction, but does the bottom differentiate to some multiple of the top? Yes. Right? Tan 2x does go to sec squared 2x some multiple. So we're going to guess ln, remember the mod brackets, 1 plus 2x plus c. There you go. That's the guess. You're so close to finishing this now. You just need to differentiate it to see if it works. So ln function goes function on the bottom, derivative of function on the top. So do I have 2 sec squared 2x on the top? No, I have minus 4. So I need to times my answer by minus 2 to make this work. So to adjust, minus 4. So not minus 4. My original answer was ln. Let's get this going. Original answer was ln. So we're going to times my answer by minus 2. So minus 2 ln 1 plus tan 2x plus c. And if you differentiate that to check, that will work. I think we've got just 2 final examples, right? Oh no, that's it. That's all done. Cool. I hope that's given you lots of examples to help with your reverse chain rule.